15'e başlayacağız değil mi?
Evet hocam. Hocam e-postanızı kapatıyorum.
İsimlerin soyisimlerin açık olduğu bir şey var mı hocam?
Hocam. Açık şekilde yok hocam.
Yok değil mi? İki kere iki oldu.
Ya da hocam bir program.
Var mı? Benim bir şey var. Şuradan başlayalım.
Program getirmen lazım. Program getirmen lazım.
İsim yok ya. Kaybolan nasıl zaman?
Ben bilici.
Evet. Ben de getirdim. Ya sen bana
Bir not kağıdı getirir misiniz hocam? Birkaç tane not kağıdı.
Welcome, everybody. We are in OC of GAZİ. For the first session, we have 4 topics for speakers. Let's start for wasting any time. First speaker is Vildan Bilici, but he is not here. She is not here, I think. The presentation will be done by Ayhan Erol. Please, you can start.
Thank you very much. 15 minutes, all right. Bassak herhalde açar.
Ses açtınız mı? Açtınız değil mi?
Sesimiz, her şeyimiz açık. Görüntümüz
Tamam,
açık.
görüntü de var.
Kendimi görüyorum zaten. Şeyi açayım istedim de. Ha. All right, good morning, ladies and gentlemen. Thank you very much for coming to listening me, my presentation. Actually, today our topic is examination of electroless nickel coated silicon nitride ceramics by ultrasonic pulse echo method. First of all, I like to say that I am a researcher about the composite materials. I mean, I'm trying to produce good composite materials and using the techniques, the powder metallurgy. At the same time, I mean, as you all know, many techniques you can use for produce the composite materials. We using powder metallurgy and also we use electroless nickel coating techniques. So today, maybe we can say 3 main things that I can mention. I mean, producing material using electroless nickel coated methods. I will explain it, how it is, and also characterization and ultrasonic technique. So, if you look at the contents, introduction, materials and methods, results and discussion, conclusion. So I have 15 minutes. I hope I will finish in that time. I don't want to spend my time to talking about the literature review because we all researchers and scientists, so we all know about the ceramics like silicon nitride. So I mean, silicon nitride, of course, is a nitride ceramics and very important material for the industry, for composites and others because of heat resistance and hard material as well. The problem is, the ceramics problem, general problem is to giving shape for the ceramic. It's not easy as metals. So that's why, I mean, today I like to talk about coating techniques and why we use the nickel for the silicon nitride. For what? I try to explain it, and how we add this nickel to the composites. Maybe I will read this part, this paragraph, because it's talking about the ultrasonic testing pulse echo technique. So in this study, ultrasonic testing pulse echo technique, which is one of the most preferred NDT techniques for the characterization of material properties from destructive, semi-destructive, and non-destructive testing techniques, was used for material characterization. I mean, of course, we all know again, we have the many techniques to characterize our material, our sample, using the different techniques. And most important things to not giving any damage to the material. So this technique is the best technique because you don't destroy your material just using techniques. For example, if you use the hardness technique you should use that, how to say, I can't remember the English, you giving a little damage to the sample. So instead of that, you can use just these techniques and then get the same result. Why not? So ultrasonic technique testing parameters are significantly affected by change in microstructural or mechanical properties of materials. I mean, if you produce the one composite material, you have to characterize and also give the identify. I mean, you should give the properties of the material. What did you produce? And what is it? And how is it? You should explain it. So that means you have to give, after producing the material, you have to give these answers. Thus, change in one or more for easily measurable parameters associated with the passage of a high-frequency sound wave through a material transit time. Attention change in physical properties such as hardness, elastic, modulus, density, homogeneity, or grain structures. When we doing this research, we have a colleague from the physics departments, and she asked us to use these techniques. Generally, we use in the normal hardness techniques. All right, materials and methods. Yeah, that is the point I like to talk about, electroless nickel coating techniques, because all we know many nickel techniques, and these are electrolysis, electrolytic, and this is electroless techniques. That means there is no any electrical current, just the chemical things, chemical baths. So I will give the recipe of these chemical solutions. In order to improve the properties of materials produced by the powder metallurgy method, first of all, powders, I mean silicon nitride, as you see in the slide, were coated nickel by electroless method. Thickness of all the samples is approximately 5 millimeter, and diameter is just 30 millimeter. A composite formed with silicon nitride was prepared under argon cover in the temperature range 1000 and 1200 with a 50 Celsius degree temperature increase. I mean, if you again producing the composite material, you should find the application and what is the advantages of this composite material, why we using this. So during the producing time, the criteria is you should think about I mean taking time. For example, if your producing time is taking too much time under oven and using any atmosphere, any gas like argon, is also financially is affected you. So what you need to find a way, low temperature and shortest time to use and produce the material. And then you will get good composite. If you get that, then you can sell it easily and find the application. So we used sintering temperature 1000 and 1200. I mean, I didn't talk about powder metallurgy techniques. All we know how to use the powder technology, powder metallurgy. I mean, sintering techniques. And there are many different sintering techniques. using it. In this time, we just use the liquid sintering techniques, because if you compare the material we use in silicon nitride and nickel is melting point is lowest than silicon nitride. So for electroless nickel coating, we use these chemicals, and ratio is nickel chloride powder form, hydrogen hydride. I mean, this is little different than the other electroless nickel coating techniques. I mean, generally people use sodium phosphide or kind of techniques. But in this technique, if you use in hydrogen hydride and this formula, then you can get the pure nickel instead of any ingredient. So distilled water and pH value has to be 10. I mean, after this slide, I will try to explain how we did it. So ultrasonic measurement, the equipment is here. Sonates side scan 550 flow detector. We use that. I mean, you send in the sound and is hitting and coming back. And you have to measure. I mean, actually, it's automatically from the computer is measuring it. And then you can find if your composite have some pores or other things, then it's not coming very fast. So that means, and you can say something about your composite material. This is porous composite material. This is the main point, actually, aim of this study. Yeah, as you see in this graph, how it is working. Samples, as you see in there. Hardness measurement. After the sintering process, the samples were left to cool naturally in the oven, and hardness measurements were performed using Vickers hardness tester. Macro hardness measurements were made at 10 different points and hardness measurements. That means if you're using Vickers hardness, at least 10 points you have to take the measurement. So that's why it gives little, even little is damage. So that's why we like to use these other ultrasound techniques. I mean, before passing the results and discussion, I like to talk about, because our colleague from Georgia, they using the electrolysis techniques, nickel plating techniques. Maybe I will give some information about the electroless nickel coating. It will give idea for their work. So, I mean, as you see in the chemical ratio, you have to prepare this. And I mean, in my study, I used several ceramic materials, like carbide ceramics, silicon carbide, tungsten carbide, so on, and nitride, as you see in here, silicon nitride, and oxide, aluminum oxide, alumina ceramics. And also, not just ceramic material, you can use even, you can put even any metal as well, like aluminum. I mean, in the past, I used silicon carbide and aluminum metals, mix it and put it in that chemical bath and adjust the pH 10, heat it, and then nickel coatings from the nickel chloride, nickel comes out, that reaction, and then that nickel stick into your ceramics or metal elements. So if you sorry, And let me finish because already 15 minutes passed.
Please,
But no, I didn't finish. Sorry, just resolve and I will read it very fast. I mean,
presentation. Any questions? Finished?
Chairman, he doesn't allow me to finish. Yeah, as you see in the results and discussion on the slide, like there, actually, I like to show graph and then it will be. For example, we used 1000, 1050, 1100, 1150, 1200 Celsius degree temperature, synthetic temperature. And then hardness, weak gas hardness, we measured, and what we found maximum, for example, 1200, we get 156 hardness weak gas, we get it, and porosity is 26.1, and density is very low. So this is the graph, synthetic temperature and ultrasonic velocity wave. So you can see in the graph. I mean, when we get from hardness weak gas result and we use this ultrasonic technique, gave the same result. So that means we are on good way. It is not false, and that's why we continue to use it. And this is another graph. Conclusion, silicon nitride ceramics with high porosity were produced by electroless nickel coating method, and their elastic properties were characterized by ultrasonic measurement. Nickel coating is preferred because it facilitates the sintering of silicon nitride ceramic powder by providing homogeneous coating and at the same time prevents oxidation. The relationship between ultrasonic sound wave velocity and sintering temperature, hardness, porosity, and density was investigated. The obtained values and results showed good agreement with the literature values. The highest density in the composite, in the composite made from nickel and silicon nitride powder sintered 1100. The highest density, which is 7.41, and again 1100 Celsius degree temperature. The highest hardness 1200, as we've already seen it. Powder metrology technique. It was also found that the composition of silicon nitride showed the best properties at 1200 Celsius degree. Right. Thank you for listening me. If you have a question, I will do my best to answer it.
First of all, thank you very much for this presentation.
I mean, yeah.
This tiny question, I mean,
Of course.
it's not, I mean, just obvious for me. So regarding the relation between the density of the thickness, I think, and the temperature, I saw it's for 1000 there. It's a little bit increasing to 1050. You can go there.
Yeah.
That, table. But later on, it actually changed. The relation is not always the same. Can you just go back? Yeah, this one.
Yeah.
You see now at 1000, we have 6.22, then 7.08. Then again, we have 7.4. Then 6 again. So you see, 6 comes again with 1150. So it's like not directly proportional to the temperature.
I see what you mean.
You just want to highlight on that.
Yeah, actually, I mean, this, for example, silicon nitride and nickel, if you look at the phase diagram, 1155, you can get nickel silicides. This is very good intermetallics material. So mechanical properties is, if you compare with others, very good. Like nickel aluminide. So, I mean, if you increase the temperature, I mean, about the powder metallurgy techniques, because sintering that liquids is going around to get in when it cold, when get compact. But sometimes you cannot get it perfectly. That's why, I mean, sometimes different get, and also, as I mean, I mentioned it, 10 times we getting the result from the one sample. Maybe in that time is not the perfect place to get the result. This is the point. That's why actually we want to use ultrasonic technique. Thank you.
Okay, thanks again. I have a short question. What about sample and application? Is it applicable for the industry?
Actually, this is one of our master degree students' thesis, and this is the one part of this work. We didn't give all the work here. I mean, as we know, the ceramic metal composites used in different area in the industry, but I can't say to exactly you can use these things to do here. Just a research for the literature review. But I hope in the future we can find a good application and we can sell it. Yeah, then we can be rich. Thank you.
Thanks.
Okay. Thank you.
Şeyde mi? Ne olmuş ya? Bakmam gerekiyor. Buradan mı şeyde mi? Uğraşıyor. Bakmam gerekiyor.
Fatma Nur Hocam merhabalar. Bizi duyabiliyor musunuz?
Evet, duyabiliyorum hocam.
Merhabalar. Bir kez daha konuşabilirsiniz. Sesinizi alalım biz sizin.
Merhaba.
Merhabalar Fatma Nur Hocam. Ekran paylaşımınızı yaparak hocamızın sunumlarından sonra sunumunuza başlayabilirsiniz.
Hocam ben dün mail atmıştım. Sesimi kaydedip MP4 formatında.
Mail atmıştınız. Hangi adrese mail atmıştınız hocam?
ICMATSE24.gmail.com.
Özür dilerim. Tekrar söyleyebilir misiniz?
ICMATS Kongresi'nin kendi mailine. ICMATS@gmail.com.
Anladım. Şu an ona çok erişim sağlayamıyorum hocam. Ben yeniden mail atmanızı rica etsem farklı bir yere ben hemen buradan indirsem.
Çok iyi olur hocam. Ben hangi mail adresine atayım?
Geçebiliriz aslında şunu konuşmak.
Üçüncü konuşmacımız burada mı? Bence yok. Üçüncü konuşmacımız bence yok. Bence yok. Şöyle yapalım. Fatma Nur Hocam.
Macit Soboro. Macit,
Fatma Nur Hocam ben buraya mail adresimi yazıyorum.
Tamam.
Görebiliyor musunuz?
Sohbete yazdınız değil mi hocam?
Sohbete yazdım evet hocam.
Ha, şu an geldi evet.
Tamam hocam oraya atıyorum
Hemen
lütfen.
gönderiyorum.
Daha önce görüşmedik. Nasıl? Ben hocam bu Karbon Mühendislik Gazı'da kimya çektim. Yani bundan önce 3 sene oldu. Buraya 3 sene oldu. Sedat Hoca'yla. Boren geldi. Görüştük mü bilmiyorum. Orada başkan yardımcısı 8,5 başkanım.
Ekranı kapat.
Borla ulaştık geldiler.
Bunu da kapalı.
Bizim Nikel Bor kapladık. Bizim çalışmalarımız var. Yapalım da bunları orada
Gönderdiniz mi hocam?
Ben gönderiyorum.
Ne olacak? Bizim bu arayı kapatılınca artık kaçar. Siz
Ankara. Ama 25 yıl İngiltere'den sonra.
yabancı gelmiyorsun. Anlamayacağım da. Nereden hatırlıyorum bilmiyorum ama konferans. Siz hocam
Ben Afyon'dayım. Başkanım beraber.
Ben gönderdim.
Gönderdiniz.
Evet.
Mail kutumu kontrol ediyorum hocam.
Öyle Adem hocalar da bunlarla çalıştı.
Peki hocam bunu sizin oradan yönetmeniz daha kolay değil mi Fatma Nur hocam?
Şimdi
Hocam hazırlık yapmıştık. O yüzden
evet, ama işte
sorun olmazsa.
Yani bizim buradan slide geçmemiz gerekecek anladığım kadarıyla
Yok,
sizin.
hayır. Geçmemiz gerekmiyor. Video formatında yüklü. Kendi kendine ilerleyecek.
Ha, video formatında.
Evet, evet. Evet.
Mailinizi bekliyorum. Hala gelen kutusuna düşmedi hocam.
senin için e-mail'den falan bekliyorum.
E, gelmediyse ben buradan
Vakit var, iki geçirsek.
videoyu açayım o zaman.
Yokmuş. Acele etmeyeceğiz.
Öyle olur mu hocam?
Hocam tekrar söyleyebilir misiniz?
Eğer hala gelmediyse ben buradan videoyu açayım. Öyle olur
Hala
mu?
gelmediyse
Ben
Videoyu
buradan
buradan açayım diyorum.
hazırladım.
videoyu siz oradan açsanız daha iyi olur aslında
Tamam.
hocam, evet.
Tamam.
Ekran paylaşımını
Bizim yerimiz var.
Hemen yapıyorum.
açtınız mı hocam videonuzu?
Hocam hemen açıyorum.
Vakit rahat. O yüzden sıkıntı yok.
Hocam paylaşım yaptım. Gözüküyor mu şu anda?
Şu an görünüyor hocam. Ben de
Siz Berat Üniversitesi'ndesiniz. Georgia Teknik Üniversitesi.
hocam şu an görünüyor. Evet. Fatma Nur hocam.
Tamam. Dilediğiniz zaman başlatabilirim.
Teşekkür ediyoruz hocam.
Ben teşekkür ederim.
Kamera kapalı, ses açık.
Okey. Fatma Nur hocam, beni duyuyorsunuz.
Evet, duyuyorum.
Okay, the second topic. Sorry. Okay. Development of nickel-based bimetallic anode catalyst for direct ethanol fuel cells. And the speaker is Fatma Nur Tiran. You can start, Fatma Nur hocam.
Thank you.
Dear attendees, search for sustainable and clean energy continues rapidly worldwide. In this context, low-cost and environmentally friendly energy solutions are gaining more and more importance every day. I am Fatma Nur Tiran, and I am very excited to present to you today our study on direct ethanol fuel cells, which we have been conducting together with Professor Dr. İrfanar and Dr. Yavuz Yağızatlı. Our study aims to make significant contributions to low cost and sustainability as an alternative solution to green energy. I will talk about the types of fuel cells, direct ethanol fuel cells, the types of direct ethanol fuel cells, comparing co-catalysts for ethanol electroxidation, selection of catalyzers, synthesis and characterization method, and analysis results. Fuel cells are a system that produce electrical energy through the electrochemical reaction of the fuel and the oxidant, resulting in oxidation and reduction reactions. They use three main components: a fuel, an oxidant, and the electrolyte. Fuel cells are a thermodynamically open system. Fuel cells which do not need to be charged convert the energy produced during reaction directly into the electrical energy by electrochemical means during the reactions shown in the figure. Electrons move through an external circuit, which provides electric current. Protons pass through the electrolyte to the cathode. At the cathode, electrons and protons combine with oxygen to form water. The table shows the most common fuel cells. Compared to these fuel cells, direct liquid fuel cells can operate longer and with higher performance. can be produced from environmentally friendly source and can be operated at low price with appropriate catalysis. Direct liquid fuel cells generate electricity using a variety of fuels such as methanol, ethanol, etc. And only byproducts such as water and heat are generated in the process. The fuel cells consist of three basic components: anode, cathode, and electrolyte membrane. Ethanol entering from the anode is oxidized by the platinum-based catalyst and split into electrons and protons. The electrons generate electricity and protons migrate to the cathode and react with the oxygen molecules of the air entering the cathode to form water. Direct ethanol fuel cells have some advantages over other liquid fuel cells. Direct ethanol fuel cells has higher energy density, can store more energy, can be produced from renewable resources such as biomass and agricultural products. Ethanol is less toxic and safer for human health than some fuels such as methanol. Ethanol produced environmentally harmless products such as water vapor as a result of oxidation. Fuel cells, which were discovered in the early 19th century, were first produced at Cambridge University in 1932. These fuel cells are alkaline fuel cells that produce 5 kilowatts of energy. Over time, this subject has been developed for use in many devices. As seen in the table, it can be used in vehicles, portable devices, and many electronic devices. As a result of all the research, one of the biggest challenges to the commercialization of fuel cells is cost. The high-cost noble metals such as platinum, palladium, and ruthenium used in the anode are economically disadvantageous. Moreover, these noble metals have poor tolerance to carbon monoxide poisoning. Therefore, our study was conducted with the aim of finding the most suitable catalyst for fuel cells. Electrochemical analysis and characterization methods were applied for the determined catalyst. For catalyzed preparation, the nickel, cobalt, and copper metals in nitrate salt form were reduced by the co-participation method. These metals were treated in ethanol in certain molar ratios under atmospheric conditions for 48 hours. The resulting solution was kept at 75 Celsius degrees until the solvent evaporated. The remaining soil-like structure was first dried in an oven and then calcined to stabilize the structure. A catalyzed layer was prepared with bimetallic catalyzed naphtha solution, ethanol in prepared molar ratios. Cyclic voltammetry, current amperometry, linear wave voltammetry, and impedance spectroscopy were applied to synthesis catalyzed as electrochemical experiment. XRD, FDR, semi-DX, and nitrogen adsorption were preferred as characterization methods. In this section, we will see the result and discussion of electrochemical experiments and characterization studies. Cyclic voltammetry graph of all catalysts with different mole ratios is shown in the figure. CV helps to understand the redox behavior, reaction kinetics, and catalytic activity by measuring the Q-response of the system when the potential cycle is entered. When the oxidation peaks seen in the forward scan section of the graph are examined, the nickel-copper 9010 catalyst gives the highest peak in the ethanol reaction. The oxidation peaks seen on the anode side represent the electrochemical oxidation of ethanol in the literature. When we look at the oxidation peaks, we see that the nickel-cobalt catalyst with a ratio of 70-30 has a high current density, meaning it shows better catalytic activity. When we look at the graph, the activity increases as the cobalt ratio increases. Nickel and cobalt metals have low slopes according to Zaffer graphs and therefore high oxidation rate. In addition, we accelerated the formation of intermediate and the oxidation of products. For this reason, a comparison was made when the nickel-cobalt 50-50 catalyst was synthesized. However, it can be said the optimum ratio in nickel-cobalt catalysis is nickel-cobalt 70-30 shows us forward sweep data in the cyclic voltammetry test. By comparing the highest peak with the nickel-copper 9010 catalyst and pure nickel, the scenario of nickel and copper was tried to be interrupted. In the chromoamperometry graph, the current drop indicates activation as a result of reaction. Nickel-copper has the highest initial current test for the 90-10 ratio catalyst. This result also supports the cyclic voltammetry results. At the end of the 1000 second, the current drop is relatively small for all catalysts. This indicates that the stability of the catalysis is suitable. The 90-10% nickel-copper catalyst has the smallest radius, which means less charge transfer and higher. The results support other chemical experiments. The bonds found in the FDR analysis for nickel-copper catalyst confirm the desired catalyst structure. Peaks between 400 and 600 wave numbers on the fingerprint indicate metal oxide titration. The peak intensity occurred between these wave numbers. Bonds observed at wave numbers approximately 2900 and 2800 are attributed to carbon-hydrogen bonding. Wave numbers around 1400 and 1000 may represent carbon oxide bonding. Similarly, when looking at the graph of nickel-cobalt catalyst, the most common peak range is seen between wave numbers 400 and 600. These bands mainly represent metal oxide bonds. Some characterization tests were performed to understand the structural morphology of the nickel-copper 9010 catalyst, which gave the highest catalytic activity as a result of electrochemical tests. The sharp and high-intensity peaks in the XRD graph indicate that the catalyst has a highly crystalline structure. This is a critical feature that increases the activity of the catalyst and provides the desired reactivity. According to the literature, the sharp peaks observed at 2 theta angles are nickel oxide peaks. It's observed that the surface consists of densely dispersed particles. A homogeneous distribution is observed, which is the positive sign for the catalyst activity. Larger structures and voids are observed on the surface. These voids can facilitate the excess of reactants of the surface. No agglomeration is observed in the image, supporting the activity results. The oxygen seen in the ADX table was observed due to the contact of the catalyst with air. The nickel and copper ratios are 72:9, conforming to the mole ratio of 9:1. Nitrogen absorption-desorption analysis was performed to understand the structural properties of the nickel-copper catalyst in detail. All isotopes show a sharp increase in relative pressure, indicating the presence of macropores. A hysteresis look greater than 0.2 was observed, indicating the presence of slate-like mesopores. The gradual increases in the volume of nitrogen absorbed with increasing relative pressure indicates a significant surface area. This hysteresis loop observed here is similar to type H4, which is usually associated with slate-like pores. As a result of all the research, it was revealed that one of the biggest difficulties in commercialization fuel cells is cost. High-cost noble metals, such as platinum, palladium, ruthenium, used in the anode are economically disadvantageous. Moreover, these noble metals have a poor tolerance to carbon monoxide poisoning. Therefore, our study was conducted to find the most suitable catalyst for fuel cells. In cyclic voltammetric graphs, the best catalytic activity was given by the 9010 nickel-copper catalyst. Electrochemical impedance spectroscopy supports the cyclic voltammetry results with the lowest diameter ratio. According to the Kernow parametry results, the best stability belongs to the 9010 nickel-copper catalyst as expected and supports other electrochemical analysis. The XRD pattern shows nickel oxide peaks with high molar mass and indicates that the catalyst is crystalline. FDR results indicate the density of metal oxide bonds with the most intense peaks. In some ADX analysis, it is seen that the structure is homogeneously distributed. No agglomeration is observed. Nitrogen absorption-desorption results report type 4 hysteresis. Characterization results show the reasons for the high catalytic activity of the synthesis catalyst. Thank you for listening.
Okay, thanks for your presentation. Let's pass to questions. We can take questions if there is.
Yes,
Please.
just to make it correct, Fatma. Thank you, Fatma, very much
Okay.
for your
Thank
presentation. You can hear me, yes? You can hear me?
No.
No?
Can you please come closer, please?
Oh,
Yes. Sorry. We can.
okay, Fatma.
Okay, thank you.
Now you can hear me, yes? So
Yes.
thank you very much again for your presentation. And really, it's very good for the students to know all these details. Yeah, thank you. Fatma, regarding choosing Kaba, okay, attached to nickel, because you said nickel Kaba, which is 9010, yes?
Yes.
This will be the best choice, okay? And instead of using the expensive, materials. My question is, did you check it for, many trials? How long you store it or check it? And then you can see the effect as the time passes. Because copper usually it gets oxidized, So is there any challenges due to that? Or is just you look from the performance for a short time? That's my question. Is it clear?
Actually, it is not clear to me. Sorry, I don't understand. Can you repeat, please?
It's not clear. So
Uh,
slowly.
Yes,
So
yes.
you said that you use nickel copper. Copper is نحاس, copper, Cu. NiCu. 9010, yes?
Yes.
Okay. So any challenges, any copper due to the oxidation, corrosion?
Maybe, sorry.
Anladın mı Fatma? Fatma Hanım?
Tam olarak duyamadığım için ses çok...
Öğrenci değil Fatma dedim ama Fatma Hanım anlayabildin mi?
Hocam ses çok kesik kesik geldiği için
Şu
yani çok...
kabalt demiyor değil mi? Kaba ne oraya kaçırdım ben ama kobalt,
No, nickel copper, Cu.
kabal, Cu. Cu diyor yani çok kolay oksidilebilen bir malzeme. Zaman geçtikçe uzun zamanda bu çok daha rahat okside olur. O dolayısıyla böyle bir problemle karşılaştın mı? Böyle problem yaşadın mı diyor. Güzel bir seçim yapmışsın diyor, tamam. Ama çok güzel, best, çok iyi bir seçim ama böyle bir problem var. Uzun zamanda problem okside olur diyor. Yani böyle bir problem yaşadın mı diyor.
Actually, we will investigate later. We don't perform it in that study.
Oh, I see.
We will
Okay, so I think you need to do that. You have to check for us for a long time. So maybe you see the challenges. Thank you.
Okay, thank you again.
Thank you.
Then we can pass to third speaker, but I think he or she is not here.
Speaker isn't here now.
So the fourth speaker is Dr. Ali.
Ms. Fatma, you can stop sharing your screen. Dr. Ali, you there?
Can you hear us? Bekliyoruz. Şimdi konuşacak. Muhtemelen
Okay.
böyle bir problem var.
Hello, Dr. Ali, can you hear us? Hello. Dr. Ashraf Ali, can you hear us?
Yeah, I'm Professor Ashraf Ali. Yeah,
Okay,
I'm hearing.
Professor. Okay, Professor Ashraf Ali, now it's your turn.
Okay, you have 15 minutes. You can start, please.
Now
Our
I can.
presentation. If you hear us, you can start your presentation. Okay.
Okay. I am in the schedule. My time was starting at 12:20 p.m., which is 3:20 p.m. From Bangladesh. That's
Yes,
why
yes, but program is a little turned. If you are ready, you can start your presentation with sharing screen.
Okay, now.
Did you share your screen?
Yeah.
It's okay.
Is it okay?
Yes, we can see, and you can start, I think.
Thank you very much, dear session chairs. I would like to also thanks the organizers for inviting me to this prestigious conference. The title of my presentation is the Rise of 212 max-phase borides with enhanced thermomechanical properties. Before going to my presentation, I would like to introduce my university with you. The name of my university is Chittagong University of Engineering and Technology, which is from Bangladesh, and one of the 5 technical university in this country. This university also known as the Green Paradise. We can see the large number of trees in our campus and like a deep forest. And the Department of Physics is housed in this building of Chuet. This is the oldest building at Chuet. And now I'm going to my presentation. This slide shows the content of my presentation. At first, I would like to say about max phases, then the structure of 212 max phase borides, which is the main focus of my today's speech, and the properties of max phase borides, and also I would like to compare the properties with 2 unknown phases. That's why we call that enhanced mechanical properties or thermomechanical properties, and application of some max phase boride or max phases, and lastly some of our ongoing projects. At first, introductions. Actually, my first question is what is a max phase? The max phase actually consists of layered ternary carbide or nitrides, which is known as max phase. But the general formula is n plus 1 xn. Previously, M element was usually taken from the transition metal, and A element from the A group element, and X element is either carbon or nitrogen from the periodic table. But max phase have very unique properties which combine ceramic and metallic properties. For example, like metallic properties, they are good conductor of electric. They have very good electrical and thermal conductivity. They are machinable, and they have good elastic properties. And like ceramic materials, they are lightweight. They have very good oxidation and corrosion resistance. They have also very good elastic properties at high temperatures. Due to these combined properties, max phase are usually known as ceramic metals. And currently, max phase have been expanded largely, and a total of around 524 max phase compound have been known so far. And currently there are 28 M elements and 28 A elements as well as 6 X elements. This periodic table shows the mapping of M element, A element, and X element. And due to these, the interesting properties of max phase, scientists are always try to expand the max phase family. That's why a large number of max phase compounds have been explored up to now. And as well as scientists are always also try to expand this family by extending their structural features. The structure of max phase is also a point of research to the scientific community. And one of them is the discovery of MAP phase, which is also which is belong to the orthorhombic systems, and max phase are belong to the hexagonal systems. But these MAP phase actually the scientists started to vary the max phases structure, and they found these type of map phase. And map phase also exhibit similar properties of max phase, like combination of ceramic and metallic properties. And recent addition to this max phase family is the discovery of 3-on-4 max phases as well as 2-on-2 max phases, where X element boron has been taken. And the 2-on-1 or 3-on-4 max phase is slightly different from the previously known max phases. The max phases of crystallize, both max phases crystallize in hexagonal systems, but they have two different space group. This slide shows the unit cell for 2-on-1 max phase as well as 2-on-2 max phase as well as 2-on-1 max phase. As we can see that there are difference in the atomic positions. The significant difference is that in 2-on-1 phase, that is a previously known max phase, there is only one X position, that is a boron here. And the boron elements are there. There are 3 layers of boron, but due to symmetric positions. But in the 2-on-2 max phases, there are 2 boron positions, as we can see here. And there is an interstitial boron atoms within this boron layer. This is the significant difference between these two structures, and due to the existence of these layer and the interstitial boron atoms, a very strong covalent bonding between the boron atom within this layer is formed, which significantly enhance the stability as well as properties of 2-on-2 phases compared to 2-on-1 phases. As already I have said, the properties of max phases, that is, it is a max phase exhibit a combination of metallics and ceramic properties, like lightweight, oxidation, corrosion resistance. That is why max phases are called as ceramic metals. Now my question arises, why they are called ceramic metals? Because of these 5 reasons. If we analyze the structure and bonding of the max phases, we can find that there is a strong overlap between P state and X element, and the D states of M elements. The M means max, M from max and X, this max and X, leading to a strong covalent bond. That is, there is a strong covalent bond between M and X element. Covalent bond. This covalent bond is mainly responsible for the ceramic properties, and the density of states at the Fermi level of the max phases is substantial, certifying the metallic nature. Another reason is that there is also a weaker covalent bond. This is weaker than compared to M and X element. Between the M and A elements. Though these covalent bond is not found for all max phases, but MX covalent bond is present for all max phases. This covalent bond is comparatively weaker than this previous one, and the electronic state above the Fermi level are mostly DDM orbital. If we see the electronic band structure, and in the max phases, there is a net charge transfer of charge from M to the X element, which is responsible for the ionic bonding. Due to these five reasons, max phase exhibit both metallic and ceramic properties, which can be shown from this. This is the electronic band structure and density of states of 312 max phase borides compounds. Actually, these compounds we predicted, and the last 3 months ago, this had been published in Helium Journal. And from this band structure, we see that strong overlapping of valence and conduction band. This is the certificate. This is the typical nature of metallic compounds, and this is the density of states from, and we see that there is a finite value, DOS value at the Fermi level, which certifying the metallic nature also, but we can see from the partial density of state that there is a strong hybridization between different atomic states. For example, if we consider that this belong to the titanium d orbital, and this belong to the boron p orbital, and these two orbital hybridize significantly, and this hybridization between titanium and boron is contributed to form a strong covalent bond within the max phase. That is why max phase exhibit both ceramic and metallic properties, because this usually we know that covalently bonded materials are exhibited ceramic properties. The existence of ionic bonding can also be confirmed by this table. This is the atomic population analysis. From these tables, we can see that in this table we can see from both 212 and 21 on max phase. This is 212 max phase boride, and this is 21 on max phase boride. And from this table, we see that the charge of boron, titanium, and phosphorus. Boron have negative charge, whereas the titanium and phosphorus both have a positive charge. Positive charge means we can consider that some charges have been released from titanium and phosphorus, which is accepted by the boron, so which is the evidence of the existence of ionic bonding within the max phase materials. And from these tables, we see that for both 2-on as well as 2-2 phases, both ionic bonding is present. And let's have compared the properties of 2-on and 2-2 phases. As my title is Rise of 2-on-2 boride with enhanced physical thermomechanical properties. That means I have to compare the properties with 2-on phases, and density is one of the criteria to be compared. And normally max phases are lightweight. That's why they have potential applications in many fields, such as transportation, particularly for airplanes or space vehicles. As structural elements, light materials are required for these types of vehicles. And from these two tables, we can see that both materials, 2-on as well as 2-2, have low density, that is, they are lightweight. As we can also consider the 2-on phase with 2-2 phases, and we can see that they have very close density. Suppose Ti2 phosphorus carbon and Ti2 phosphorus carbon, there is no carbide 2-on-2 phases. For 2-on-2 phases only there is boride phases till now. That's why we cannot compare the 2-on-2 boride phases, 2-on-2 boride phase, 2-on-2 carbide phases with 2-on-on carbide phase. But there are some 2-on-on boride phases. That's why we can compare both of them. I'll show the next slide. Mechanical properties, usually max phase have very good mechanical properties. Their Young modulus are usually 300 gigapascals, and their Vickers hardness are usually within the range 2 to 8 gigapascals. That's why they are relatively they exhibit soft nature, and they are also machinable because of their soft nature. This slide shows a comparison of the mechanical properties of 2-on-on and 2-2 phases. The C1-on, C33, C44 are the stiffness constant, though there are other 3 stiffness constant for max phases due to their hexagonal nature, but I have shown here only these 3 constant for comparison. And if we see that for 2-on-on phases and 2-on-on phase and 2-on-2 phases, here we have shown we can see a comparison with both 2-on-on boride as with 2-on-2 boride, as well as 2-on-on carbide with 2-on-2 boride phase. And if we consider this for phases, Ti2 phosphorus B2 compared with Ti2 phosphorus boron, we can see that each of the parameters of 2-on-2 phases is higher than those of Ti2 phosphorus boron phase. If we consider this niobium 2 phosphorus B2 and compared with niobium phosphorus B, then we can also see that the parameters of 2-on-2 niobium 2 phosphorus boron 2 is significantly higher than those of niobium 2 phosphorus boron. There are also a comparison among the boride and carbide. If we consider this hafnium 2 indium boride phase and with hafnium 2 indium carbide phase, then we can also see that a significant enhancement or improvement is shown for 2-on-2 phase compared to 2-on-on phases. And also we have included here the hardness parameter, which has been calculated by these 2 formula, AH chain and AH meow et al. And these hardness parameters also significantly higher for 2-on-2 phases compared to 2-on-on phases. Already I have seen that I have said that max phases are relatively soft with Vickers hardness 2 to 8 gigapascals. This is the one of the experimental results. This is not our result, published results, and this table shows our results. These tables include both 2-on-on as well as 2-on-on as well as 2-on-2 phases. If we consider that, we see the table that the max phases are almost within the range of expected range. And due to these hardness values, we can say that the phases are soft. And also, we have already said that max phase exhibit ceramic properties, and ceramics are mainly brittle class of materials, and these brittleness of the ceramics or max phases can be checked by these 2 parameters, Pop ratio and Poisson's ratio, and there is the critical values given here. And from this table, we can say that the max phases are brittle class of materials, so though some of them is ductile. For example, molybdenum 2 gallium boron is ductile according to this parameter. Some of carbide max phases have also been found as ductile materials and can be found in insects. There are some reports on the ductile max phase carbides. And usually max phase have fracture toughness within the range of 4 to 8 megapascal. This is the experimental values, but we have no facility for max phase synthesis as well as measurement. So we have to characterize theoretically, and we calculate the fracture toughness values using this formula, but the limitation is that this formula is for purely covalent bond, and there is another formula which is purely for ionic bonded materials. But since max phase has a combination of metallic and ionic as well as covalent bond, so none of the equations effectively calculate the fracture toughness values, and our calculated values are much lower than the experimental expected values. But we can consider we can compare the values with 2 on 1 and 2 on 2. From these tables, there is a 2 on 1 phase, zirconium, gallium, boron. The fracture toughness of these 2 on 2 phase, such as zirconium 2 carbide, germanium B2 is significantly higher than its counterpart boride. Then coefficient of thermal expansion, which is a very critical parameter for high temperature technology. As we know that max phase have very good max phase are very potential materials for thermal barrier coating materials. And for thermal barrier coating materials, there has one of the critical parameter is a coefficient of thermal expansion, which is lies from this figure. We can see that usually max phase have thermal coefficient of thermal expansion within the region of non-oxide ceramics and oxide ceramic and thermal barrier coating materials. And for a good thermal barrier coating materials, the coefficient of thermal expansion should be comparable to those of thermally grown oxide, which is usually grown at high temperature environment, and metal substrate or any others which should be protected by the thermal barrier coating materials. And due to the very good coefficient of thermal expansion of max phase material, they have very good prospects to be used as TBC materials. We have also calculated some CT values of some 2 on 1 as well as 2 on 2 max phases, which is also though lower than the experimental values. Obviously, these are the experimental values, and our values are totally theoretical or calculated values. So there is a significant difference among the values, but we can consider the values. And due to these values, we can also expect that the max phase, either 2 on 1 or 2 on 2 phase, have perspectives to be used as thermal barrier coating materials. And we can consider the thermal properties of 2 on 1 and 2 on 2 boride phases. One of the important parameter is Debye temperature, and from table we can see that we can see a comparison of 2 on and 2 on 2 phases. For example, Ti2 phosphorus B2 can be compared to this Ti2 phosphorus boron or Ti2 phosphorus carbon, and we can see that the value is significantly higher than that of 2 on both boride as well as carbide phase. If we consider zirconium-2 lead boron or niobium-2 phosphorus boron-2 or zirconium-2 indium boron-2, for each of the cases, we can see that the divide temperature of the 2 on mixed borides are significantly higher than those of 2 on phases. Another important parameter, thermal parameter, is the melting point. As we have frequently said that max phases are potential candidate for use in high temperature technology. Therefore, they should have a very high melting point, and we have also calculated the melting points. And from this slide, we can also see that the melting point of 2 on phases is significantly higher than those of 2 on 2 phases is significantly higher than those of 2 on phases. Each of the 2 on phase exhibit a higher melting point compared to their 2 on phases. Another typical parameter is minimum thermal conductivity. Since max phases are can be used as a thermal barrier coating in high temperature technology. Therefore, the thermal conductivity at high temperature must be very low, and the materials with lower value is better or more suitable than other. In this case, with that, we can see that the 2 on phase, some of the 2 on phase exhibit lower K minimum value. Suppose Ti2 phosphorus B2 have lower K minimum value compared to 2 on phase, suppose Ti2 phosphorus boron or Ti2 phosphorus carbon. Similarly, zirconium lead B2 have lower K minimum value compared to zirconium-2 lead boron. That means the thermal properties and also previously shown the mechanical properties both are better for 2 on 2 phases compared to the 2 on phases. Machinability, though max phases are brittle, but due to the existence of ionic bonding within them and metallic bonding, they are also machinable, and they can be formed in different shapes. That's why we have also calculated the machinability index, and the 3 colors show 3 different patterns. The green color shows that the machinability index of 2 on 2 phases has a larger value compared to 2 on phase. And the black color shows very low variation among the 2 on 2 and 2 on phases. And in the red color, we can see that some of the 2 on 2 phase exhibit lower machinability index compared to their 2 on phases. From this table, we can say that most of the max phases, 2 on 2 max phase exhibit better machinability compared to their 2 on phase. Electronic properties, if we consider the electronic properties of both 2 on and 2 on 2 phase, we can see a similar band structure and density of state. These are the band structure and density of state for 2 on 2 phases, and this is the band structure and density of state for 2 on phase. And we can see from these both slides that both 2 on and 2 on 2 phase exhibit metallic nature and very similar electronic characteristics among them. And another application is the parameter is the reflectivity. Already I have shown in the table where I shown that material has a light weight, and I told that they have application in airplanes or space vehicles. In that case, if some of the max phase exhibit a very good reflectivity, which is usually 44% or above. It is reported that if any max phase that exhibit a reflectivity above 44%, then this phase can be used as cover material or coating material to protect the space vehicle from the solar heating. And max phase have two both. This is the this curve is two on two phase, and this is the two on phase. And we can see that both two on as well as two on two phase exhibit a very good reflectivity, which can certify that these phases can be used as coating material to protect the spaceship from solar heating. Though some other parameters have to be considered, but just I have mentioned here one of them. But interesting to note that in this case, two on two phase exhibit better reflectivity than two on phases. Now the question is, why are thermomechanical properties of two on two phases enhanced? The answer lies in these two unit cell structure. If we focus this structure, we can see that for two on two phase, that is left figure, there is a 2D boron layer at the center position, which is sandwiched between two M elements. And within this boron layer, there is a strong covalent bond, and this bonding level or degree of level of covalent bonding is much higher than which is formed for two on phases between M and X element. Our statement can be proven by this table. Here, some of the two on two phase and two on phases. First one is two on two phase titanium 2 phosphorus boron 2. Here there is a rightmost column exhibit the bond overlap populations, and the value is a higher value is usually indicate higher level of covalency, and lower value is indicate lower level of covalency. From these column, we can see that the BB bonding, first row for Ti2P-B2, BB bonding, which has bond overlap population of 2.47, which is much higher compared to its counterpart part Ti2 phosphorus boron. If we consider Ti2 phosphorus boron, the strongest covalent bond with bond overlap population is 1.10. Though there is another covalent bond with population is 0.96, but for two on two phase there is also another population with bond overlap population is 1.0. That is the bond overlap population for two on two phase are much greater or significantly higher than those of two on two phase. If we consider each of the pair of two on two and two on phase, we can see that for each cases, the bond overlap population for BB bonding or boron-boron bonding is much higher than those of strong covalent part in two on phase. Suppose niobium boron is a significant difference is there. That is why another important parameter is the bond length. We know bonding strength also depends on the bond length. Higher, larger bond length means comparatively weaker because of their larger distance among the atoms. So if we focus on the bond length, again we can say that the bond length between BB atom is significantly lower than the lowest bond length in two on two phase. For example, Ti2P boron, the lowest bond is 2.27, whereas for Ti2 phosphorus B2, the lowest bond length is 1.82. These lower bonding is smaller bond length and higher bond overlap population significantly contribute to the formation of stronger covalent bond for the 2-on-2 phases in comparison with the 2-on-1 phase. That's why the mechanical properties of 2-on-2 phase is significantly higher, as we have already seen previous slide, compared to the 2-on-1 phase. And we know that the thermal properties are strongly correlated with the mechanical properties because that's why, due to the enhanced mechanical properties, their thermal properties are also significantly enhanced for the 2-on-2 phases. Some of application can be shown from the max phases. If we consider a gas turbine engine that have two parts, hot parts and cold part. In the hot section, these structural elements can be made from the max phase material due to their high metallic melting point, and they have very good mechanical properties at high temperature. And in the combustion chamber, there are some elements that can be protected from further higher temperature, and that's why there in this region some thermal barrier coating material have usually used. And in this section, max phase can also be used as thermal barrier coating materials. For example, as a heating element, titanium, aluminum, carbon-based heating element frequently used, and it can be heated at up to 1450 degrees centigrade in air. The high temperature coating material is one of the potential application of max phases, and we have already seen that max phase have very good coefficient of thermal expansion. They have a high melting point, and they have reasonably high mechanical properties at high temperature. And that's why max phase can be used as thermal barrier coating material. Max phase can also be used and bond coat material, because max phase easily joined to different material by solid state diffusion method, which can be seen later. Another application of max phase is
Sorry, Dr. Ali, please complete your presentation within a few minutes, since time is over.
Okay, please, just 5 minutes. Okay.
Okay.
In this case, max phase can be used as thermal storage tanks, and this is the mechanism by which max phase can be joined to different ceramic metals, ceramic and metal and metal. And another very deep, recent application of max phase is the precursor of magazine. Many max phase can be converted into their two-dimensional counterpart, which is known as magazine, and the application of magazine is very well known to us, and I have skipped this. And some of our ongoing project with max phases, prediction of M2 AB, from this project, one of the article has been published. This is another. These are the ongoing project in our labs, and we have a very good research groups. I am Professor Ali as the principal investigator, and my collaborator, Professor Saleh Hassan Nakib sir, Professor Mohiuddin, Professor Nusrat Jahan, and Dr. M.D. Mukhtar Hussain. And we have some students, PhD, we have PhD student, MPhil student, and MSc students. And we have already established a computational materials research laboratory with the fund of TAWAS, and some of the Since my focus was the range of 212 max phase boride, and so far we have already published 4 papers on these materials in different journals, which are very reputed journals. And one of them is also submitted in Material Advance, published by Royal Society of Chemistry. And in addition, another 2 different max page material, 3 on 4 max page material, have also been published from our groups. These are some of our papers which have already been published in different journals in recent years. Thank you very much. We all always welcome collaborator for building a bond with us. Thank you very much.
Okay. Professor, we thank you for this good work and nice presentation of it. Let me take questions if there is any. No questions. Then thank you, Dr. Ali, again for your presentation.
Thank you very much. Also, both to you for inviting me in this prestigious conference, especially Professor Gökhan Surusu, who invited me. And he is also one of my collaborators. We already have published one of the articles in SAS Omega. Thank you, everyone.
Okay, thanks. Let's finish the session. We thank you for coming with us. Okay,
Okay. Thank you, everyone.
thank you.